We are Team 19067, sponsored by Mr. Carwash, and we worked on improving the water reclaim system for car wash applications. My name is Gabby Vidakovich.
I'm Elizabeth Hernandez.
I'm Annie Bratton.
I'm Derui Ma.
I'm Ahmad Ali.
I'm Canning Jin.
The goal of this project was to design a small-scale, on-site water reclamation system that cleans water for use that is generated from the car washing process to reduce overall water consumption. Currently, some Mr. Car Wash locations have water reclaim units, but few are effective. Our design focus was to address the following: odor elimination, an output of 15 to 20 gallons per minute, and implementation at a Mr. Car Wash location.
In addition to our main project objectives, there are a few other things we had to keep in mind. Our system had to run on the adequate power of a standard 3-pin 220-volt connector to a wall, it had to be leak resistant, it had to reduce the largest particle size in the water to be below 5 microns, it had to treat the water in the nurse tank, and it had to reduce the water's total bacterial count. These became our project's system requirements. We consulted the U of A's Chemical Engineering Department for advice on how to approach our project given the aforementioned system requirements, and they suggested using a technique called advanced oxidation, which involves hydroxyl radicals that break down contaminants in the presence of UV light. Our team had 3 options for advanced oxidation. 1, no oxidant, so just the UV light without advanced oxidation. 2, hydrogen peroxide, referred to as H2O2. Or 3, titanium dioxide, referred to as TiO2. The initial tests for odor reduction showed similar results between all 3 advanced oxidation options. Similarly, the TOC test, which stands for Total Organic Carbon Test and measures the reduction of the water's total bacterial count, were fairly inconclusive among the 3 options. However, we knew that advanced oxidation works because of our research and that the initial testing did not fully represent the system we had in mind. So with that, we decided to continue pursuing advanced oxidation for our system. However, Mr. Carwash informed us that they had tried using UV light without advanced oxidation in the past and did not get satisfactory results, so our team discarded the option. Then, more research showed that there was not enough information on TiO2 to determine if it was safe enough to integrate to a water reclaim system, given that it was such a small particle and hard to remove from the water. With all of this in mind, our team decided to use H2O2 as our advanced oxidation method.
The system consists of 3 primary forms of treatment. First, water enters the system in the green sand filter, which is a form of pretreatment. The sand filter has 2 functions. The first is to reduce turbidity, or murkiness, of the water. High turbidity is an issue in UV light because it occludes particles from the light and from getting treated. Thus, removing them with the sand filter makes the UV light treatment later in the system possible. The second function is to remove hydrogen sulfide and manganese present in the water. The hydrogen sulfide is a source of odor, and the manganese can precipitate in the presence of UV light, so it is advisable to remove it first. After the pretreatment, the water enters the primary treatment loop. This loop consists of a storage tank, 3-way ball valve, hydrogen peroxide injection, and a UVC photoreactor chamber. Water is pumped from a 30-gallon storage tank through a 3-way ball valve and into the hydrogen peroxide injection. Pumps were selected based on a 415 gallon per hour flow rate and a calculated head of about 28 feet. Hydrogen peroxide is injected with a Venturi injector, otherwise known as an eductor.
After water is well mixed with hydrogen peroxide, the water passes through a UVC light chamber. Ultraviolet rays penetrate bacteria and viruses and destroy their DNA. We create a UVC chamber with 3 lamps that have cross-layer protection on each one of them. The UVC lamps consume a total of 516 watts and output 162 watts of UV light with current regulated with 3 bullets. The power of the lamps simulates reaction with hydrogen peroxide and will be used for killing hydrogen sulfide producing bacteria. The orientation of our lamps was designed to penetrate particles from multiple directions to help the trickle issue with turbidity. The flow rate will allow each batch of water stay in treatment loop for 4.3 minutes. Water treatment depends on exposure time to the light, so our system was designed to let water pass through as many times as demanded necessary, through testing to achieve a greater exposure time.
The team created several analysis models that represent the system's behavior. First, we needed a power consumption model for us to monitor the cost of running the system. In this model, each part's contribution to the power consumption is added to the total, where the cost would be found from that total. Currently, the system consumes a total of 848 watts and costs $0.086 per hour to run. Another model we had dealt with hydrogen peroxide. In this model, we calculated the needed percent concentration of H2O2 in the UVC chamber from the flow rates of water and H2O2. The flow rates of water is mediated through the pump, while the flow rate of H2O2 is mediated through the eductor. The system needs 0.11% concentration of H2O2 and will have an operating cost of $25 per hour to run. We also had a UVC chamber model that takes the total reaction time of UVC light with the contaminated water, the number of pass-throughs, and the water flow rate to calculate the time it takes the system to decontaminate, which comes about 4.3 minutes. Exposure time was one of the key parameters in this model, since an increase in exposure time equates to a more effective system. Mr. Carwash will have to calibrate the parameters based on the facility's location. The system flow rate model calculated the treated water output for the entire system, using information collected from the UVC chamber. The entire system is estimated to output 207.5 gallons of treated water per hour. All models were created in Excel and can be scaled up.
Because of the Corona-19 situation, we were unable to complete full assembly and were unable to test the system. Looking back at the whole design process, we do have some recommendations for our sponsors regarding the system design. First, another method for injecting H2O2 into the system is essential. Currently, we use an eductor in the system, which is sufficient for a bench model scale. Ideally, Mr. Carwash would want to implement a control pump injection system that use sensors in their car wash facility to mediate the necessary amount of H2O2 into the system. Another recommendation is to add another storage tank to make an alternating system that will allow one batch of water to be treated while another is filling or discharging, increasing system efficiency and usability. This system would incorporate level sensors to control the system automatically. Depending on the condition of a given facility, the system will need to be tested to optimize the amount of H2O2 and exposure time. Even though there was a global pandemic that heavily impeded our progress on our project, we still learned many valuable lessons throughout this year.
As a team, we would like to thank our sponsors Rob Heisterman, Will Blair, and Greg Burleson, our mentor Mark Brazier, along with our faculty resources Dr. Eduardo Saez, Dr. Kit Farrell-Poe, and Dr. Greg Ogden for helping us complete this project. Thank you.